Okay, that is on. Alrighty. Welcome everyone to this week's colloquium. Today we have Sam Paudel here, presenting correlated topological phases in two-dimensional materials. So please give a warm welcome to Sam.
Hi everyone, thanks for the introduction. So yeah, my name is Sam Paudel. Just for some background, I'm a fourth year undergrad in physics, and I've been doing research with Professor Sergio de la Barrera. And so this is sort of like the main topic of my research project, and so I'll just be presenting on some of the theory and some experiment behind it. So yeah, my talk is titled Correlated Topological Phases in 2D Materials. So just for a brief outline, first off, I'll start with some basics of solid-state physics. So that includes a lattice, what electronic bands are, electrical properties of solids. I'll move on to topological phases. So that includes the classical and quantum Hall effect, if you've heard of those. I'll also talk about topology. And then towards the end, I'll be talking about interaction-driven phases, where the interactions between electrons are really important in these systems. And some examples of those are the mod insulators and also the fractional quantum Hall state. So first of all, I just want to answer the question of what a solid is. We can sort of physically tell, but on like a microscopic level, this is sort of what one would look like. It's just a periodic array of atoms. You can describe them, say, in 2 dimensions with just 2 vectors, and basically you add up each of these. So you can take linear combinations of these 2 vectors. Those numbers in front, n1, n2, n3, those are integers. And so that's how you define a solid in real life. Now, these solids, I said they're periodic. And so whenever I say that, you might be thinking of Fourier series, if you recall from maybe second year, where you expand a function that's periodic with a period t, let's say, f of x. We can expand it in terms of sines and cosines, where the frequency of the function depends on the period of whatever you're looking at. And so now in 2D, it's a little bit different. So here we'll be summing over vectors. We have some coefficients ag, and then we also have these exponentials, e to the igx. And these two, they are equivalent. You know from Euler's theorem that we can just write these sines and cosines in terms of exponentials, and that's what we get. But now the question is, which values of g should we use? And so to do that, we define what's called the reciprocal lattice. Similar to how for the periodicity, given a periodicity, we can define a bunch of frequencies that we sum over. Here, given a bunch of lattice vectors that span the entire lattice, we can define some more vectors. So here we have b1 and b2, and they're defined by this property where the dot product with the actual lattice vectors are 2 pi or 0. And so visually, this is sort of what this would look like. On the left there, you have real space. That's what you would see visually. This is a triangular lattice. So if you were to imagine, maybe squint your eyes a little, connect the dots between the nearest points, you see this is just a network of a bunch of triangles. And so if you just apply this formula, work out the algebra, you'll get what's on the right there. So these are all the vectors that you sum over in your Fourier series. And so after we have this lattice, we can define what's called a Brillouin zone. So we saw before, if I just go back, on the left, that triangular lattice is period, but on the right as well. And so from this periodicity, turns out we can just look at a little segment of our reciprocal space. So in this red dot here, or this red region here, these are technically defined as just all the points that are closest to the origin, and that are closer to the origin than another reciprocal lattice point. And so we can just look at all the physics that happens in this little region, and then we can just repeat it over and over. Now I'll talk about what's called crystal momentum. Just to get some background, by the way. So is anyone here in first year, second year? Okay, third year, and then fourth year? Okay. All right, so if you're in fourth year, second year, I guess, you might have taken physics 354, so you remember if you have a symmetry of the Hamiltonian, you get a conserved quantity. If you think of just a free particle, you have a continuous translational symmetry, and so no matter where the physics happens, you get the same results. So in that case, your linear momentum is conserved, and p, if we're talking about quantum mechanics, we'll say it's a good quantum number. So just working out the math here, from free particle, you might have learned in quantum that the wave function is just a complex exponential. It's an eigenstate of the momentum operator. with momentum h bar k. It turns out in lattices, we don't have this periodic symmetry. So you can't just move to a random place in space and say it just looks the exact same as some other place. We only get this symmetry when you move over by one of these lattice vectors, A1. And so in this case, we have a discrete symmetry, so we get this momentum result, which is also discretized. It takes on this form here at the bottom, and so nx, ny, nz, these are just integers, and then lx, ly, lz are just the length of the crystals along each direction. So now I want to talk a little bit about dispersion relations. In solid state physics, we also call these we call them bands, electronic bands. So if you remember, just for a free particle, the momentum, if you have a momentum p, the energy is p squared over 2m. So the energy is h bar squared k squared over 2m. Now, imagine you have a bunch of these. So if you have, say, I don't know how many dots this is, say about 20 electrons in the system, right? I just showed before that this momentum is quantized. So you have little dots. So at each value of k, you get a state. It has particular energy. And so you can, one by one, just fill up these states. In this picture, it looks like somewhere around 20. Yep. One by one. It's a great question. So um, electrons have this thing called they obey the Fermi direct distribution. So that's, they're also called, it's related to the Pauli exclusion principle. So this is where two electrons can't be in the same state at the same time. Compared to something like a photon, you can have a bunch of photons with the same energy, but for electrons, you just can't. And so if you fill these up one by one, you get to some energy. We'll just call this EF, which is a Fermi energy. And so it turns out that the position of this Fermi energy in the dispersion or band actually dictates all of the electrical properties, a decent amount of them. So one example is, say you have a system that has a valence band and a conduction band. If you've taken chemistry, if you remember, you'll have valence orbitals, the outermost electrons, and then any electrons with energy greater than that, they'll just be floating around in the crystal. They'll be free electrons. And so depending on whether an electron's in the valence or the conduction band, um, it'll either contribute to the conductivity or won't. So on the left here, so these two pictures are just sort of 1D and then like a 2D representation of what you might see. So all the way on the left, that's a metal. That's the case where these two bands, they're overlapping on top of one another. Semiconductor where you have a small gap, and then insulator where you have a large gap. So from that you can tell if you have your Fermi energy somewhere inside of a gap, you have no conduction electrons, and so you won't have any conductivity. So now, remember from first year, Ohm's law, V equals IR. This is sort of in a circuit. If you have a potential difference across it, potential drop, in a resistor, you'll get a current I. Turns out it's a little more complicated. So if you're in higher dimensions, say you're looking at the current inside of a 3D solid, the current J, or more specifically the current density, it'll be related to the electric field through some constant. Here, sigma, it's the conductivity. Since these are vectors, the most general relationship we can really give that's linear, that makes life easier, is a matrix. So if we just write it more so in the form of the top equation, we'll have this relationship at the bottom here, where the electric field is related to the inverse of the conductivity times the current. The inverse of the conductivity, resistivity, that's what we call it. And it has this general form of a 2x2 matrix in 2 dimensions. So with that, now I want to move on to the next segment. This is all the background, sort of what we'll be applying to these systems. So I'll start off with these topological phases. So first of all, I want to consider this system here. This is a top-down view of a 2D metal. So we have a magnetic field here pointing into the page. Now we just imagine if we have this 2D sheet of metal, we have a current going across it. We know from the Lorentz force law, we'll get a deflection of these charged particles, right? So you can work it out with the right-hand rule. It turns out that these electrons move upwards. So it turns out that whenever we applied a current along the horizontal direction, we actually get this electric field in the vertical direction. Well, that's not something we would expect, right? If you sort of think of a similar problem, imagine we had an electric field pointing in this direction, you'd expect that the electrons would flow in that direction. This is a little different. And so that's where the idea of this transverse conductance and resistance comes in. Remember in the resistivity matrix, we had these 4 entries. Um, it turns out that this rho xx and rho y, these are going to be the values that we observe when we measure it in an experiment without any magnetic field, and rho xy and rho ix, they'll be just 0. The way you can interpret these quantities each here is how the system reacts when you apply an electric field. So, back a bit. Right. So these entries for rho relates E equals rho j, right? So if you have this quantity here, if you have a current in the y direction, what's the resulting electric field that you'll get? That's what this means in the x direction. Similar for this entry here, if you have a current in the x direction, what's the electric field you'll get in the x direction? So going back here, if we work out the math, it turns out in this 2D system with a magnetic field, um, you get these quantities, rho xx and rho yy, they're the same, they're just some constant. The details aren't too important. But then we have these two here on the off diagonal. So this means that it agrees with our observation from before. So if you apply an electric field in the x direction, you'll get a current in the y direction. It turns out it's proportional to B. So these two components of the resistivity matrix, they're very different. And one of them might be intuitive, the other one maybe not so much. I'll talk about this a little bit more when I go into the microscopic quantum explanation of this. It turns out that when you turn up the magnetic field even higher, you'll actually get these plateaus. Now, this isn't what we saw before, right? Before, we just had a constant for rho xx, and for rho xy, we had a line. Now, it turns out that's what you see down here. So you'll see there's a constant here in the black that represents rho xx, and then it's linear in the magnetic field for rho xy. So this is very interesting. We've never seen this. This is what we call the quantum limit. This corresponds to very low temperatures and also very high magnetic fields. So the microscopic explanation for this is through these cyclotron orbits. So thinking again about the Lorentz force law, um, you can imagine there's some electrons, you apply a very strong magnetic field, right? What happens is that each of these electrons will travel in loops. So you can just see that here. Using right hand rule, you have V in this direction, B is pointing into the page, so you get a force radially inwards. If you repeat that every point along the circle, you'll just get a circular orbit. And so this is going to remind you of harmonic oscillators in 2 dimensions. And so this is why that's been drawn here. So in the middle, you have all these electrons going in circular orbits. But something interesting happens along the edges, actually. So on the edges, you can imagine electrons trying to go on a circular orbit, but it hits this wall here. There's nowhere for it to go right out here. It's a vacuum. So what happens is it gets scattered backwards, and then it continues in this loop. So turns out what happens is on the inside, it's actually insulating. So there's nowhere for these electrons to move. They'll be insulating here, but on the edge, you actually get a circular current forming. This is what we call an edge state, and these are very robust. You can imagine, right? If an electron can only move clockwise, if it were to say hit some impurity at the edge here, if it wanted to go backwards, it would have to cross the entire entire uh, solid state, whatever you're looking at, whatever 2D sample, um, and that's very unrealistic. This is on the scale of, say, like centimeters, right? You won't have a single electron going across. And so this is what we call a topological insulator. It's an example of this, where the inside is actually insulating, and on the outside you get a current flowing. Now, to explain this, there's this concept called Landau levels. It turns out, so if you imagine these electrons, this is their energy versus momentum relationship, their bands, right? Um, as you increase the magnetic field, I said that it looked like a bunch of harmonic oscillators, and so that's exactly what you get. You get these levels. These are very flat, and each of these are spaced out by a constant amount. And so that constant amount is related to the frequency of this harmonic oscillator. Now, if we look at this on what's called a density of states plot, so this basically, you can just think of the density of states as the number of available states within a band at a particular energy. So energy is a vertical axis. Say this is your energy. By the way, this doesn't exactly map here, but it's just a visual comparison. At this energy, the density of states is 0 because there's no energies, but here at some value, here at some value, it's also 0 here. And so as we turn up the magnetic field from the left to the right, this is what the energy looks like. These are called lambda levels, each of these bumps here. And so whenever we're in a bump, if you go back 10 or so minutes when I told you that if the Fermi energy is inside of a gap, you'll get a resistor. And so as we continuously move from the left side to the right, you'll notice that the Fermi energy is constant because that's just, the Fermi energy is just dictated by the number of electrons in the system. Remember when we were filling up the parabola. And so at some point, you'll be changing the bands around, and you'll go from a conducting state to a insulating state, conducting, insulating, and so on. Now we have this quantity here. We'll call it nu. This is the filling fraction. It's the number of these bumps that we've filled up with chemicals. And so that relates to this idea of these plateaus. That explains it actually. So as we go up in magnetic field, we'll have these. Each of these plateaus here corresponds to when we fill up one of our lambda levels. And so the exact relationship is that the resistivity here, the red curve, it plateaus at values of h, which is Planck's constant, divided by e squared, charge of an electron, divided by this filling fraction nu. And so so when we have, say, one lambda level filled, we're here, 2, 3, so on. And that explains why at the very low magnetic fields, we only see a linear dependence. And that's just because as nu gets really, really large, this thing linearly just goes straight to 0. Now, I want to give you a new perspective on this. I'll introduce the concept of topology in these systems. So from topology and mathematics, there's this concept called a Chern number. It's the integral of this quantity here. It's called a Berry curvature. It's just some number that you define at every point in reciprocal space. So every point on your band, and you just sum it up over entire band. It turns out that it's always going to be equal to an integer. And so this is due to what we call the topology of the bands. I can talk a bit more about that later if you're curious. But these topological invariants, they're very robust against external perturbations. It's a property of the system, and oftentimes these are what we call symmetry protected. So these systems have symmetries, and it's very hard to break these symmetries easily. So relating this back to lambda levels, it turns out that the filling fraction is related to the number of lambda level, or the Chern number of the lambda levels that are filled. So going back to this plot, over here, the filling fraction was 6, and we say that at this point, the total Chern number is also 6. So that means since each of these are integers and there's 6 bumps here, each of which is a band, that means that each band is a Chern band. It has this topological invariant assigned to it. Now, I want to look a little bit at the symmetry associated with this Chern number. So the quantity that we were integrating over the Brillouin zone, this Berry curvature, it has a couple of specific properties. The question I really want to answer is, why did a magnetic field create topology? Right before, we didn't have anything. We just had a plain metal, but somehow turning on the magnetic field actually generates these topological bands. So under spatial inversion and time reversal operations, so what that means is that for spatial inversion, you take x to minus x, y to minus y. It turns out that the Berry curvature is the exact same. If you take time to negative of itself, so if you replay the physics exactly backwards, so physically that would say instead of an electron going from left to right, it would go from right to left. Turns out that the Berry curvature picks up a negative sign. And so this means that, say you perform these operations right on your system, spatial inversion, time reversal. Now, if you want these symmetries to be respected, that means that both of these quantities have to be 0. So for a number, for a number to be equal to the negative of itself, of course, it has to be 0. And so this means that the Berry curvature that we had before in these lambda levels, we can generate them if we break one of these symmetries. The question is, how do we break these symmetries? So in a real system, there's a few mechanisms. So on the left two here, these are sort of scattering off of impurities. So if you could imagine some sort of impurity in your crystal, it could be something that you don't want, say, in a carbon or like a diamond, in a piece of diamond made of a bunch of carbon, but you could have a piece of silicon in there, just randomly spread out. That's just how crystals are in real life. And so off of this, they somehow couple to the spin. So depending on the spin of the electron, it'll deflect in one of the directions. There's another type where it just, instead of changing the direction it's moving along, it'll just provide a little kick, like either up or down. And then there's this third one called the anomalous velocity. It's very strange. It's also very unintuitive. If you have an electric field pointing in some direction, these spins, they just naturally will deflect towards one direction. And that's really not something you would expect. The electric field couples to the charge, but somehow the spin, like magnetic property, is also related to the electric field. So for this anomalous velocity, turns out you can show, it's a very long derivation, but at the end, what you get is that if you have an electron in the nth band, some band, you'll get some velocity, it's a constant, but you get this term out here at the end. So omega n, that's just the Berry curvature of the band. And so this is a connection between the topology and also like a physical phenomenon, which is directly observable. So if you have some finite Berry curvature in your system, you will get a physical deflection of these spins depending on whether they're up or down. And so in this system here, this is sort of what it would physically look like. You have a current, has a bunch of random electrons. We can't really control this. Some are up, some are down, but depending on whether you have Berry curvature or not, some of them go up, some of them go down. And it turns out that if you have an uneven amount of up or down spins, you'll get an uneven amount of charges on either side, and then you'll generate this Hall voltage again. So now I want to talk about the quantum anomalous Hall effect. So in the anomalous Hall effect, what happens is that time reversal symmetry, what we like to call, is spontaneously broken. This is due to an intrinsic effect. The intrinsic effect is something that is not due to an external sort of parameter like the magnetic field. And so this system, it'll break time reversal symmetry. And in this case, what that means is, you can imagine, these spins are what we call time reversal partners. So you can imagine a spin as a dipole, right? A magnetic dipole comes from a current loop. And so if we turn the current around in the opposite direction, then you'll get the opposite magnetic moment or the opposite spin. And so this results in a polarized, or in a spin polarized edge current. So this current will flow in one direction. And so it's clear in this case that if we had time reversal symmetry, there would be equal amounts going in the clockwise versus counterclockwise direction, but we don't, because we've broken time reversal symmetry. Another interesting thing that happens is we get magnetic hysteresis. So if we plot the resistance as a function of magnetic field, actually depends on the direction that you're sweeping. So if you're increasing B, you'll get this dotted line here. But if you decrease it, you actually get a completely different curve. This is shown as a function of temperature. So if you're at 4 Kelvin, you won't see any of this. As you drop down, you see this curve, and then the hysteresis starting to show. And so this shows that these effects really are only visible at really low temperatures. So now I'd like to talk a little bit about how we actually break these symmetries in real systems. So I'll be talking a little bit about 2D materials. This is what I've been doing my research on. These 2D materials are layers of atoms held together by very weak interlayer forces, but the bonds within each plane are very strong. So you can imagine this as sort of like a blanket almost. You can like pull on it, it won't like rip, but if you have a bunch of blankets sort of stacked on top of each other, you can just drive one off. and you can isolate these very easily. And so it turns out these bands that can be controlled directly using electrostatic gating. So this is sort of a device geometry here, and this is what you'd see in an experiment. That's sort of what I've been working on in the lab. Um, if you apply some voltage across these, you'll get an electric field, and so that can actually control the shape of these bands directly. So to break symmetries in, say, graphene, for example, that's a system that I'm studying, a array of a hexagonal lattice of carbon atoms. There's a few techniques you can use. So one of them is combining materials. So if you have some other 2D material that doesn't have inversion symmetry, so this is a bit more of a concrete example of inversion symmetry. If you were to imagine just this sheet that's pink and purple, pink and blue, if you were to choose this point and invert everything about that, so you reflect everything about the origin. So the blue point goes here, this one goes here, and then this one goes here. You can see that the crystal that you end up with isn't the exact same thing as you started with. So that breaks inversion symmetry. Another thing that happens is with just two graphene layers, although you might expect that because each of these graphene layers has this inversion symmetry on its own, it turns out that once you stack them on top of each other, they actually don't. This is what it ends up looking like. So you get these triangles. Um, this is also on a really large length scale, so this is 100 nanometers in the scale bar here, but the size between, or the distance between these atoms on the atomic scale is around like a third of a nanometer. So this is a very large scale symmetry breaking. And so we can just see this case here, say this is your inversion point. If you flip this, you won't get the exact same crystal. Now another third option is interactions. So it turns out that at really low temperatures, when these interactions become important, they can also break symmetries, and that's what I'll talk a little bit about later. So for these interaction-driven phases, this is where really low temperatures and these interactions, you can actually see the effect of them. And what I mean by interactions is just the Coulomb repulsion between these electrons. I want to start off with a more intuitive situation before we go to the full picture. So let's say we consider a free particle, right? There's no potential. Um, we have this dispersion here, so energy is p squared over 2m again, but this particle can have some mass, m star, right? It doesn't have to be an electron. But for each value of the mass, we'll get a different curve. So going from the red to the blue to the green, this is increasing mass, so the curvature actually gets lower and lower. It turns out that once we increase the mass a lot and it gets very heavy, we'll end up at this purple curve here where it's completely flat. So that corresponds to infinite mass of this particle. And so if we apply this to a crystal, we want our bands to be very flat, right? If we make our bands flat, that'll be basically the same thing as having the mass of the electron be infinite. So it's going to be moving really slowly. And so when it's moving slowly, we can study these interactions, right? It turns out that the Coulomb energy, it will be much greater than the kinetic energy. So a picture I sort of used to understand why this happens is if you're imagining two planets, say, orbiting around each other, if they're moving really fast, they're just gonna fly off in their own directions. But if they're moving really slow, such that their energy is lower than the gravitational attraction, then they'll be orbiting each other. And so that's sort of the interactions that I'm talking about. Um, I also want to remind you about the superposition of waves. So maybe in second year classical mechanics, you sort of talked about adding two waves together. So if you add two cosines of two different frequencies, you apply this formula, you'll get a cosine, the sum of the frequencies and a difference, right? And physically, this is sort of what it looks like. You get this large scale like envelope and then a faster oscillation inside the envelope. And so we can do that in 2D systems actually. So with graphene, this is what it looks like physically. If you have two layers of graphene and you twist them relative to one another, just as a function of this angle, this is actually what you get. And so if you squint your eyes a little bit, especially at lower angles, you can see that the periodicity is very large, right? So at 0 degrees, it's small, and then you get this large scale pattern that starts to appear. Now that's what happens in real space. If we look at the bands, this is actually what happens. So this is changing the angles from maybe around half a degree up to 1.5 degree, somewhere in that range. And you see something very interesting happens. These bands actually flatten in graphene. And so going back to what I was just talking about a few minutes ago, these flat bands means that these electrons are very heavy. And so interactions become really important. So with this, as we strengthen these interactions in these systems, turns out that these bands are not as useful as they initially were. It turns out that when we're calculating these bands, we ignore a lot of the details just because it's really hard to actually consider them when you have like 10 to the 23 electrons. And so, as I said before, interactions really begin to matter when we cool down the system. So a little more quantitatively, that's when the thermal energy, KBT, is about the interaction energy scale. And this is just sort of a pictorial representation. So if we had, ignoring like all interactions, you get these two bands, you add some interaction, you'll get a splitting. So initially what was a conductor, because the Fermi energy is right here, you get a insulator. Now, I want to talk a bit about quasi-particles. The question now is, how do we understand these phases, right? They have 10 to the 23 electrons. They all depend on each other. We really can't like keep track of all of these. So I'd say the idea is to imagine a new particle. So using this as a sort of representation of, say, electrons moving in a solid, right? Um, we have two options. One, we could either consider every single water molecule sort of moving around these bubbles, and then say there's some places with no water where these bubbles are. Or alternatively, we could think of just we have water everywhere, and then we have a few bubbles moving through the water, right? So that's way easier of a problem, even just visually, if you're thinking about it, right? You're not going to be keeping track of where the water is moving around the bubbles. You just see that the bubbles are moving upwards. So in a solid state system, what this looks like is this. So imagine we had silicon atoms in a lattice. Each of them were sharing two electrons between them. Now imagine there's one impurity, so boron. It has one less valence electron, so there's an electron missing here in this bond. Now, the option is we have all these electrons here. We can imagine them moving around, or we hold the electrons in place and imagine just this vacancy of an electron moving around. So that's what we call an electron hole, and that's used a lot in solid-state physics, especially for understanding semiconductors. Another example, a little more abstract, is spins. So if you were to imagine a bunch of electrons just sitting on a lattice, they all have a spin, and say they're moving around, rotating. Um, if you're looking at each one individually, it doesn't really make sense. But if you sort of visualize a vibration almost just moving down this line of atoms, that that can also be considered a quasi-particle. It looks like a wave, but from quantum mechanics, we know like wave particle, you can sort of draw a connection between them, and that's what we call a magnon. Now I want to talk about the fractional quantum Hall effect. So if you remember the plot before, we had a few plateaus when we looked at the resistance as a function of the magnetic field. We had a few plateaus at integer values. But it turns out if you look really, really close, you'll get a bunch more. So you have all of these. The resistivity is proportional to 1 over this filling factor nu. And so the ones we saw before are when nu is equal to 1, 2, 3. There's a bunch of these outside as well when you go to really large magnetic fields. As it turns out, these quasi-particles in this case, they have fractionalized charge. So instead of just the electron charge, you get a third of it or a fifth of it. They also exhibit what's called anionic statistics. So if you've taken a stat mech, you'll know if you have a fermion, you swap them, you get a minus sign, boson, nothing happens. Where it turns out for anions, these quasi-particles, you get a phase. You don't get plus or minus one, but you get a complex number. And the quasi-particle in this case, it acts like an impurity almost in a plasma. So if you were to have a plasma and you place some electric charge in the middle of it, that's sort of what it acts like. All these electrons are like a liquid moving around it. So just to conclude, in the presentation we talked about how the periodicity of the lattice allows us to understand these solids and their electronic properties. There's also various Hall effects, and these show a bunch of connections to topology. And how these topological bands that can be engineered by us in the lab just by combining various 2D materials. And it really just goes to show how these 2D materials, especially twisted ones, are a great platform for studying strong interactions, but also these topological states. So with that, I'd like to thank you for your time and open up the time for any questions.
Questions?
There's one back there.
So like what is the topology? Like is it like the number of holes in like a donut or something? Like what's the number and like
Good
why is it
question.
invariant?
So you might have heard of a coffee cup, right? So there's donuts and there's coffee cups. Um, so in the mathematical sense for topology, um, what we say is, imagine you had, say, a donut and then coffee cup. So you have these two objects. Just say they're in 3D space, right? Just a bunch of points. In the topological sense in mathematics, we say these two are equivalent. Now visually looking, they're not the same. It turns out that if you were to imagine these things as like Play-Doh, you could just like squish them together and continuously just sort of morph this into that. In this case, we have, so similar to this in the sense how a Chern number in a band is topologically invariant. In this case, you have topological invariant being the number of holes. So these two things here, in either case, you have one hole and any like transformation on this thing, you won't like get rid of, you won't increase or decrease the amount of holes unless you like rip this thing apart, which would be some sort of non-discontinuous transformation.
Thank you so much for the presentation. Could you go back to the slide where you first introduced the quantum Hall effect?
Yep.
The one with the conductivity graph with the peaks.
This.
Yeah, that one. And you said that whenever you fill a Landau level, you get a peak. Could you explain that again? I didn't quite understand.
Whenever I fill a Landau level, sorry.
You said that
Mhm.
there's a new conductivity like peak every time you
Right.
fill a band. Was it?
Yeah. So just going back to this picture here. So every time I fill a peak, it sort of corresponds to this this energy diagram sort of moving up, right? So it's sort of like just stretching this thing. That's what we're doing as we increase the magnetic field. And so each of these, um, each of these contributes to the total conductivity um, in a in this way. So when I said the filling factor, this is just the number of these humps that are filled, right? And so each of these contributes h over e squared. And so as you fill up one of these, you'll get another h over e squared, and another one, and another one. And so that's sort of what I mean by. Yep. So you asked about conductivity. This is resistivity. So if we were just to invert this, right, we'd have sigma xy equals e squared over h times nu. So this is, which is equal to e squared over h. And then say, if we filled up like 3 of these, right? So as you fill up one, you get one of these, fill up another, you get another one, and then so on. And so for each peak, you get some amount of conductivity. Does that sort of answer your question? Yeah, exactly. Yeah.
Well,
One question.
one person.
So these fractions, There's a theory called composite fermions. I'm not too familiar with it, but the idea is that instead of considering just electrons filling up like a single particle band, right? You'll have almost this quasi-particle spectrum. So this band structure, but for these quasi-particles. And so you'll have, say, like when I was drawing the density of states for the quantum Hall effect, each of these had like a turn number of 1. It turns out for, say, these composite fermions, each of these have a turn number of like 1/3, let's say. So this is the composite fermion spectrum. And so as you fill 1, fill 2, all the way up to this point, you'll have a turn number of 1/3, basically. And just connecting this back to the single particle picture, say your Fermi energy is all the way up here, right? You'll have a total turn number of 1. And so this corresponds to, say, filling some larger band here with electrons. So these are sort of the same picture. It's just a question of whether you're filling up a bunch of electrons, filling up these smaller subbands with these composite fermions.
Thank you so much, Sam, for your
Thank you.
presentation. Can we get another round?